at 3:27 in the morning. On August 6, 2010, a mountain in western Canada fell apart. Not with an eruption, not triggered by an earthquake. It simply collapsed under its own weight. 53 million cubic meters of rock unzipped from a 2,600-meter peak and accelerated into the valley below. The impact generated seismic waves equivalent to a magnitude 2.6 earthquake, registered on instruments as far away as Alaska and Washington. It moved at over 230 kilometers per hour, the speed of a high-speed train, and when it slammed into the opposite side of the valley, the debris washed 270 meters straight up the canyon wall. A major river system was dammed in an instant. The Geological Survey of Canada recorded the event, but for hours, in the remote darkness, no one knew what had just happened. But here's the detail that tells the real story. The rock that failed was not solid granite, it was rotten, and the ice that had held it in place for millennia was no longer there. This is the story of a volcano that does not need to erupt to be one of the most dangerous mountains in North America. To understand what is happening, you have to understand the geology of Mount Meager and the clock that is now ticking faster than ever before. The event began on the south flank of the Mount Meager massif, a cluster of glacier-clad stratovolcanoes 150 kilometers north of Vancouver. A secondary peak, weakened by eons of internal heat and acidic water, finally gave way. The initial failure was a rock slide, a catastrophic peeling away of the mountainside. It fell into the valley of Capricorn Creek, impacting the water-saturated ground and instantly transforming into a debris flow. A slurry of rock, mud, and water moving with unimaginable force. It's hard to visualize 53 million cubic meters. It is the volume of 20,000 Olympic swimming pools. And it all came down in a matter of minutes. The flow traveled 7.8 kilometers down Capricorn Creek, then funneled into the much larger Lillooet River Valley, where it barreled another 4.9 kilometers downstream before finally coming to a halt. It created a dam across Meager Creek, a tributary to the Lillooet, roughly 30 meters high. Behind this impromptu wall of rock and mud, water began to pool. A new lake, 4 kilometers long, formed in a matter of hours. Eventually, the water overtopped the dam, triggering a massive flood wave that surged downstream, destroying forestry roads, bridges, and heavy equipment. The estimated damage was 10 million Canadian dollars. But the human cost was zero. The slide happened in the dead of night, in an area so remote that only a handful of campers were anywhere near the disaster zone. They were evacuated by helicopter hours later, shaken but unharmed. It was a statistical miracle, a geologic event of biblical proportions, as volcanologist Dr. Glenn Williams-Jones would later call it, had unfolded without a single fatality. People called it a near miss, but the data shows it was not a miss at all. It was a warning shot. This is the part the headlines do not capture. The 2010 landslide was not a surprise event. It was the predictable result of a slow-motion failure that had been building for decades. Dr. Gioacchino Roberti, a geohazards expert, dedicated his PhD research to this exact problem. Using a technique called structure from motion photogrammetry, he analyzed historical aerial photographs of the mountain stretching back 60 years. He was looking for subtle changes. What he found was the smoking gun. The images proved that the slope that failed in 2010 had been slowly deforming, bulging, and cracking in direct correlation with the retreat of the Capricorn Glacier at its base. For thousands of years, the glaciers covering Mount Meager have acted as a physical buttress, a frozen wall of ice propping up the weakened rock of the volcano. As climate change accelerates, those glaciers are melting. They are thinning, retreating, and pulling back from the unstable slopes they once supported. The ice is losing its grip. This, according to Dr. Roberti's work, is what conditioned the mountain for collapse. The final trigger was simply a hot summer. Warm temperatures in the weeks leading up to August 6th caused rapid snow and ice melt. That water seeped deep into the existing cracks of the mountainside, increasing pore water pressure, lubricating the faults. The mountain, already rotten to its core, was pushed past its breaking point. It's a terrifying mechanism. Curious what you think about this, actually. And the cause of that rottenness is the volcano itself. Mount Meager is part of the Garibaldi Volcanic Belt, the northern extension of the same Cascade Arc that includes Mount St. Helens and Mount Rainier. It is a hydrothermally active system. Hot, acidic gases and water, cooked by a magma chamber deep inside the earth, have been circulating through the volcanic rock for hundreds of thousands of years. This process, hydrothermal alteration, chemically breaks down hard, solid rhyodacite into soft, weak, clay-like minerals. In the words of SFU professor Dr. Glenn Williams-Jones, who has studied the volcano for years, this big, massive mountain is rotten. It is dissolving from the inside out. For most of its history, this internal weakness has been contained by the immense pressure of the overlying glaciers. Now, that containment is failing. The 2010 slide was not an isolated incident. It was part of an escalating pattern. On July 22, 1975, a massive rock avalanche had occurred on the mountain's southern flank, originating from the Devastation Glacier. On July 29, 1998, a large debris flow ripped through the very same Capricorn Creek watershed, a direct precursor to the 2010 Mega-Landslide. The mountain was shedding its skin, piece by piece, as its icy armor thinned. Geoscientist Pierre Friel, working for Cordilleran Geoscience, had already authored hazard assessments warning of this exact scenario, flagging the immense risk that landslides from Mount Meager posed to the downstream Pemberton Valley. The science was clear. The mountain was unstable, but the true nature of what was waking up beneath the ice would not become clear until 6 years after the Great Slide. Now, here is the part nobody was expecting. On July 21, 2016, a helicopter pilot was flying a routine mission ferrying biologists to survey mountain goats on the northern side of the massif. As he passed over the Job Glacier, he saw something impossible. 3 massive, gaping holes had melted through the ice. Bizarre, dark depressions in the otherwise pristine white of the glacier, with what looked like steam or smoke rising from their depths. This was not normal melting. This was something else. This was evidence of significant, concentrated heat coming from beneath the glacier. This was proof that Mount Meager was not dead. It was not even fully dormant. It was breathing. The discovery of these fumaroles, volcanic gas vents, changed everything. The dominant threat from Meager had always been seen as gravitational collapse, landslides triggered by weak rock and melting ice. But the holes in the Job Glacier revealed an active magmatic system, one capable of driving a very different kind of disaster. It shifted the mountain's status from a crumbling relic to a legitimate eruption risk. This is a volcano whose last major explosive event, around 410 BCE from the Bridge River vent, was the most recent in Canadian history, blanketing areas as far as modern-day Alberta in ash. The discovery in 2016 meant that the engine responsible for that ancient blast was still running. It's a whole dimension of risk previously thought to be dormant. If you want to see more deep dives into these kinds of hidden geological stories, you might want to subscribe. In the years that followed, research teams began making tentative visits to the perilous new features. The data they collected was alarming. A 2022 expedition, funded by the Royal Canadian Geographical Society and the Trebek Initiative, saw a team of volcanologists and expert cavers, including Christian Stenner, rappel into the newly formed ice caves to sample the gases directly. What they found was a lethal environment. Inside these beautiful cathedral-like caves, carved by volcanic heat, the air was thick with toxic fumes. Hydrogen sulfide, the gas that smells of rotten eggs, was measured at concentrations exceeding 200 parts per million. Levels of carbon dioxide were around 5,200 parts per million. These are concentrations that can be fatal to a human in minutes. The mountain was exhaling poison. Even more recently, a 2024 paper analyzing the findings from that expedition revealed something else. Despite the toxic, acidic, and lightless environment inside the caves, life was thriving. Researchers discovered unique communities of extremophile microbes in the snowpack and sediments, organisms that have evolved to live on the chemical energy provided by the volcanic gases alone. A secret, subterranean ecosystem, powered by the volcano's inner heat, had been discovered hidden beneath hundreds of feet of glacial ice. This discovery of active, high-temperature fumaroles creates a terrifying new set of possibilities. It introduces the risk of a phreatic eruption, a steam-driven explosion. If the heat output from these vents were to increase suddenly, it could flash melt enormous quantities of glacial ice. The resulting blast could be powerful enough on its own to destabilize the already rotten surrounding rock, triggering a landslide far larger than the one in 2010. Worse, it could generate a lahar. A lahar is not a flood of water. It is a slurry of mud, rock, and volcanic debris that moves with the consistency of wet concrete and the speed of a freight train. Computer simulations using programs like HARS, which model these exact scenarios, show that a major lahar from Mount Meager would not be contained by the remote upper valleys. It would travel the full 65 kilometers downstream, and slammed directly into the town of Pemberton. This is where the remote geological drama collides with a present-day human reality. Pemberton, a town of around 3,400 people, sits directly in the crosshairs of the Lillooet River, which flows past the base of Mount Meager, runs right through the Pemberton Valley. The town's entire existence is tied to the stability of that river, and the 2010 landslide has already begun to subtly destabilize it. Researchers tracking the aftermath of the slide have found that between 2015 and 2019 alone, river erosion carried an estimated 5.8 million cubic meters of the fine sediment from the 2010 debris deposit downstream. This sand and silt is being redeposited on the bed of the Lillooet River as it flows through the Pemberton Valley. The riverbed is rising. With every millimeter it rises, the river's capacity to hold floodwater decreases. The risk of the river breaching its banks during a major storm or a rapid spring melt is actively increasing year by year because of a landslide that happened a decade and a half ago, 65 kilometers away. The community is caught in a slow-motion pincer movement. The long-term threat of a future mega-landslide or lahar looms from the north, while the immediate risk of river flooding, exacerbated by the sediment from the last slide, grows from within the valley itself, the Squamish-Lillooet Regional District. The local governing body is acutely aware of the risk. They work with bodies like the Center for Natural Hazards Research at SFU to create hazard maps and emergency plans. But how do you plan for a threat of this magnitude? How do you evacuate a whole valley when a lahar could arrive in less than 2 hours? For decades, the sheer beauty and scale of Meager's glaciers made it a hub for high-end tourism. Before the gas hazard was understood, helicopter companies would shuttle wealthy clients onto the mountain for catered lunches and parties. They set up ice-carved tequila bars and hired DJs, creating surreal celebrations on the very glaciers that were masking a lethal active volcanic system. Those on the ice had no idea what was brewing, just a few hundred feet beneath them. Low-key share this with someone who thinks volcanoes are only a problem when they burst. They were dancing on the lid of a pressure cooker. Today, scientists are using every tool at their disposal to watch that pressure cooker. Drones fly over the unstable peaks, creating ultra-high-resolution 3D models. That same structure for motion technology used by Dr. Roberti on old photos is now being deployed in near real time, allowing geologists to track millimeter-scale bulging on the flanks of Plinth Peak and near the Job Glacier. They are trying to identify the next spot that will fail. Monitoring stations listen for seismic tremors, and gas-sniffing flights measure the volcano's exhalations. There is even a push to explore the possibility of harnessing Meager's intense geothermal energy, though the prospect of building critical infrastructure on top of one of the most unstable and landslide-prone mountains in the country carries its own extreme set of risks. The 2010 landslide was an event on a geologic timescale, something that should happen once in 1,000 years. But the forces that triggered it, a rotten volcanic edifice and rapidly retreating glaciers, have not gone away. They have accelerated. Dr. Kelly Russell, a UBC professor who has studied Meager's eruptive history for decades, and other experts agree that it is not a question of if another major flank collapse will happen, but when. And the discovery of the active fumaroles adds a new, terrifying variable into the equation. The next event might not be a cold landslide triggered by weather. It could be a hot event, kicked off by the volcano's own internal heat. The water that is working to dissolve the mountain from within is now also being boiled from below. The entire system is being pushed towards failure from two different directions. So, 3 questions hang over the Lillooet River Valley tonight. How long until the next massive slide unzips from Meager's rotten flanks? Will this future event be another cold collapse? Or will the growing heat beneath the Job Glacier trigger a catastrophic eruption and lahar? And what does it mean for the thousands of people in Pemberton that with every passing year, the riverbed beneath their homes is silently rising, filled with the sand and silt from a catastrophe that has already happened? The story of the 2010 slide wasn't an ending. It was a prologue. The data shows it was the largest landslide in Canadian history by volume, but the geology suggests it was only a fraction of what is still waiting to come down. The weak, hydrothermally altered rock extends across a much larger portion of the massif. Future collapses could be many times the size of the 2010 event, large enough to create a permanent catastrophic dam on the Lillooet River, holding back a lake that upon bursting would release a flood of almost unimaginable scale. The system is primed. The glaciers continue their retreat, meter by meter, exposing more and more of the incompetent rock to the elements. The fumaroles continue to pump heat and acidic gas into the heart of the ice cap. and advanced drone surveys continue to track the ominous slow swelling of the mountainside. The 2010 event was a shot across the bow. It demonstrated the sheer power and velocity that these events can achieve, and it occurred on a slope that scientists had identified as a potential hazard. The current focus of monitoring is on other larger areas of instability that show similar signs of pre-failure deformation. The scale of the potential energy stored in these slopes is immense. The rock that makes up the mountain is not just weak, it's saturated. The combination of rotten material and high water content is the perfect recipe for long run-out debris flows, which can travel tens of kilometers and maintain devastating speeds over relatively gentle terrain. This is why the threat extends so far downstream, all the way to Pemberton and beyond. It's not just a mountain problem, it's a watershed-scale hazard. Somewhere, deep inside the plumbing of the Mount Meager volcanic complex, magma is still present. It may be miles down, but its heat is reaching the surface, a constant reminder that this is an active system. The water from melting snow and ice is percolating down, getting superheated and rising back up as corrosive steam, tirelessly working to weaken the rock. It's a process that has been happening for millennia, but is now being dangerously accelerated by a changing climate. The mountain is being unbuilt, particle by particle, from the inside out. The very foundation is being hollowed out, even as the icy scaffolding on the outside is being removed. It's a race against time, and the mountain is losing. The final signal of failure might be a swarm of tiny earthquakes, a sudden increase in gas emissions, or it may simply be another hot summer day. The water that flows in the Lillooet River today carries the memory of 2010 within it, in the fine suspended sediment that clouds its flow. That sediment is a physical link between the past catastrophe and the future risk, a constant delivery of hazard potential to the valley floor. The mountain looms over the valley, silent, white, and beautiful. But beneath the ice, it is anything but silent. It is moving, it is breathing, and it is slowly, inexorably, preparing for its next great collapse.